AP students, welcome to Chapter 18, Electrochemistry, Lesson 3. What we're going to discuss, or what I'm going to discuss with you today, or in this section, is going to be the electromotive force. Define it. We kind of already have, but we'll do it again. Relate half reactions to their voltage potentials and learn how to calculate those. We use two half reactions related to their cell potentials and predict what that potential will be of the galvanic cell, and then kind of show a simpler way to write these reactions in what's called line notation. Let's get started. So the electromotive force is actually the amount of voltage that a system will give up or has the potential for creating. So for instance, a battery has like a double or AAA battery has a voltage of 1.5 volts. That is the potential energy or voltage that could be used if the battery is actually plugged in or set terminal to terminal or anode to cathode. There would be an electromotive force, or that flow of electrons from the anode over to the cathode, and that electromotive force can be used to power some device or whatever. It is the driving force of that electron or that reaction, the pull of those electrons moving from the anode to the cathode. So it's measured, like I said, in volts. A volt is a joule coulomb. That's not really something you need to know necessarily, but that's what it is. And cell potentials with positive cell values are always spontaneous. A little different than it is with Gibbs free energy or delta G values. Those are negative, but we'll have a formula in a future video that kind of interrelates the two so you'll understand. But cell potential can be calculated a couple different, well, it's the same way, but there are different conditions. So standard cell potential that you see on a chart are standard values, and those conditions down there on the bottom are 1 atmosphere, 25 degrees C, and 1 molar solutions. That's the same as it is for delta H and delta G standard values and entropy values as well. But here, for our standard cell potentials, if you take that value off of a table, then it's going to be standard values. If you actually measure them in non-standard conditions, which would be an experiment, then those values won't be the same. And often they're not the same because in real world situations, you actually have, resistivity of the wire is what's talking about here, that carries the current would actually be less as it heats up. And so not as many electrons actually get through the system or passed from atom to atom to atom along the wire. And it reduces the overall voltage or the overall cell potential of that system. So if you look at the one that's up here at the top, this is one we use so frequently, and that's a zinc copper cell. You've got zinc immersed in a solution of its ions over here on the left-hand side, and you've got a copper metal electrode, which is the cathode, immersed in a solution of its ions on the right-hand side. And so the electrons would actually flow from the zinc to the copper. Now, if you were to set this up and try to figure out which way they're going to flow, the electrons are going to flow. They're always going to flow, so it gives you a positive cell potential, and we'll do those calculations in a moment. But in this particular case, it would give you 1.10 volts, which is up there on the top on the little cartoon, voltmeter there at the top. But anyway, so what we're going to do is take a look at that. Now, this is the same as if you went and looked at the video, or you saw me talk about this in the previous video. The zinc ions are actually going off in the solution, making the solution more positive. And so what happens is there'll be a migration of ions from the salt bridge this way, neutralizing that charge. So negative ions would move that way, and positive ions would move this way, as the copper 2 ions are actually precipitating on the elemental copper or on that cathode. All right, so standard reduction potentials, you would just look up on a chart, and you have a chart that has those values. So standard reduction potentials will be on a chart here. I think I've got it on the next page. Here they are right here, but we'll go through that in a second. But you have a chart there in your notes. The values for cell potential are usually written as reduction reactions. I guess it's possible to have an oxidation chart, but it's not. It's usually reduction potential chart. So they'll have all of them listed on that chart that are in reduction values. And some of them will be positive, some of them will be negative. In order to get an oxidation value, you just flip it. And we'll do a couple of these to kind of show you. The values are actually determined at These values are somewhat arbitrary. They're just done against hydrogen. So you set up a cell with zinc against hydrogen and copper against hydrogen and lead against hydrogen and see what that value actually is, whether it's positive or negative, and what its magnitude and voltage is. And you put it on the chart. Those on the chart, again, are standard values at 1 molar, 25 degrees C, 1 molar solutions, 1 atmosphere pressure. All the other half reactions expressed are going to be standard, like I said, to that standard hydrogen electrode. And so, oh, that's the wrong computer. And that standard hydrogen electrode value will also be on the chart, and it'll be 0. So you have a bunch of ones that are positive up at the top and then negative at the bottom. A lot of times the charts are actually written from most easily oxidized to most easily reduced. In the particular, or in this particular case, the chart that we have, the one out of the book, actually goes from most positive to most negative. It doesn't matter. You just need to know kind of what it is. Whether it's on top or bottom shouldn't really make any difference. So standard reduction potentials, if I look at this right here, what I've got is this is zinc against hydrogen. So they're bubbling hydrogen gas in this way right here. There's your H2 going in. And so the hydrogen and the hydrogen ions are where that transfer of electrons are. The hydrogen is actually forming hydrogen gas as it gets reduced and gains electrons, whereas the zinc is losing electrons. They're flowing in this way, and then they're hitting the hydrogen ions and then producing hydrogen gas. You have to have some hydrogen gas present for this to happen. But anyway, the actual metal piece of electrode that's allowing for the transfer of electrons between the ions in solution and the hydrogen gas is platinum. You would need something that is, I should say, higher in reduction potential than whatever that gas is that you're using. But platinum is pretty much inert, and so it doesn't take part in the reaction, doesn't lose or gain any electrons, and doesn't change the values here. So all of these were tested this way for the ones that are listed in the chart. So elements, like I said earlier, with very negative values are more easily oxidized. Usually, it could be that you have two that are both negative, and one of them would be switched to positive to give you a positive value. Ones with very positive values, which are typically nonmetals, but not always, but typically nonmetals, will have higher reduction potentials or more positive values. They are more easily reduced, and those that are negative are going to be more easily oxidized. The most positive reduction potential is going to be the oxidizing agent, and the one with the most negative is going to be your reducing agent. Substances with, or the more negative the reduction potential, the more easily it's oxidized, or what we call the stronger the reducing agent. So here, looking at the chart, so if I go and I try to find where is hydrogen here, there's hydrogen right there. So there's hydrogen with its 0 value. Everything here on this chart is tested against hydrogen, and those are the differences in voltages between them. The ones up here are really positive. The ones down here are really negative. The ones that are highly positive are going to be more easily reduced. In other words, they're going to gain electrons. That gives you more positive. And the other ones are going to be more easily oxidized, the negatives. So all of these over here will usually be flipped to give you a positive value. I say usually because it depends on what you put in the cells, or what you have as your anode and cathode. So let's go do an example of this. Before that, though, the cell potential, if it's positive, the reaction will be spontaneous. If it's negative, it's non-spontaneous. But if you were doing this experimentally and got a negative value, what's happened is you have your voltmeter backwards, or it's flowing in the opposite direction that you're measuring it. So you're measuring a negative cell potential, but if you flipped the leads on your voltmeter, you would get a positive cell potential, and that would be the direction the electrons are flowing. If you got a 0 cell potential, it means that you either don't have a complete cell, or you've run out of ions in solution or in the cathode region, or you have run out of your metal electrode. Your metal anode is completely corroded or is depleted. So let's do an example here. So this is going to be something that you're going to draw. So draw the cell below, and I've kind of labeled the cell a little bit here. This, well, not labeled, but this is a metal electrode here. And this is a metal electrode here. Now, typically these are done sort of clockwise, where the electrons flow in this direction through the wire. Yeah, electrons flow in this direction. And that would make the anode on the left-hand side. So I'll go ahead and write anode over here. And the cathode, did I say reactant side? On the left, and the cathode on the right. And so what I want to do is figure out which one is which. Now they've told me that I have a chromium piece of metal and a piece of lead metal, and my ions are chromium 3 and lead 2. So in solution, I'll have my ions, which are Cr3 plus, and ions over here that are Pb2 plus. So I'll also have this labeled as chromium and this one over here labeled as lead. Now you ask me, well, how did you know which one was on which side? Well, to do that, I would have to go and look and see what these are on the actual chart. So I'm going to go back up and look at where chromium and lead are on this chart. It was Cr3 plus, and be careful because sometimes look, here's Cr3 plus going to Cr2 plus. That would be an ion to ion with no chromium metal present. So I need to find the one that has the chromium metal, the solid. So here it is here. And then I'm going to go find lead solid and lead 2, and it is here. And look, they're both negative. So one of them is going to have to be oxidized. These are both listed as reduced. These are reduction potential. So I'm going to flip one of them that gives me a positive value. So it's going to be this one that I'm going to flip. That'll give me a positive 0.74. When I add it to my negative 0.13, I'll actually get a positive cell potential for the total. So let's go write those half reactions here. What I'm saying is that the chromium is actually going to lose electrons and become Cr3 plus those 3 electrons. And I think that value was 0.74. It's now positive because I flipped it, so it's positive 0.74. And the other one is going to be the lead ions as written in there, plus 2 electrons will give me elemental solid lead. I think that was 0.13. Yeah. So it's negative 0.13. 0.13. So what I'm going to do now is add the 2 together, but I need to balance the equation because it does say up at the top, draw the cell below, which we've done, label the anode, cathode. I need to still do the salt bridge. Oops. Indicate the direction of electron flow, which I've done, and calculate the cell potential and write the overall cell reaction. So I have 2 electrons from the lead and 3 electrons from the chromium. So I will have to multiply this top reaction by 2 and the bottom reaction, half reaction by 3, so that I can balance my equation in terms of charge. So if I go do that, I end up with 2 moles of chromium plus 3 moles of the plumbous ion is going to give me 2 moles. Ooh, mess up a little bit there. 2 moles of my chromic ions and 3 moles of the elemental lead. I canceled kind of in my head my 6 electrons on both sides, the 2 times 3 and the 3 times 2, because I don't need the electrons in my final equation. You do not multiply the voltages times their coefficients. If this is going to produce a certain amount of voltage, no matter what the multimole ratio is going to be. So what you're going to do is just add these 2 together. And you can determine that's experimentally. It is not like delta H, where it is the number of kilojoules per mole. In this case, it is the amount of voltage from a chromium and the amount of voltage that's going to be sort of accepted by lead. So it's not really the same. So you do not multiply them, you just add them together. And your total here would be 0.61 volts. So if I were to write it on my diagram, a little voltmeter up at the top would say 0.61 up there. And then I think the last thing I left off was the salt bridge, which in this case is kind of weird. It's got a little porous disc down there, but we'll call that our salt bridge. What's going to happen with that salt bridge is, as this chromium pops off and makes these chromic ions, negative ions are going to come in here to keep the cell neutral, which it still allows for the transfer of the charge. And then over here, you're going to have positive ions going in this solution. Whatever those positive ions are, it doesn't matter. Could be potassium ions or sodium ions or whatever, are going to go because the lead is going to pop back on here as it's reduced and gains the 2 electrons. So you guys would be expected to, yes, draw a cell like this, calculate the overall cell potential, a complete reaction of what's happening in the redox reaction, and then they go. So that's a full redox experiment right there. And we'll do a little of this in our electrochemistry lab, or you'll watch me do it, I guess, this year. But in future years, you guys will actually create your own salt bridges and set up your own cells and calculate cell potential, or measure cell potential rather. So here it is, kind of all finished up, not quite labeled, but this would be your chromium over here. This would be your lead over here, your chromic ions in here, your lead ions in here, and your electron flow in this direction. And here's your salt bridge. So is that reaction? I should have said also, it did ask whether or not, indicate whether it was spontaneous or not. It is spontaneous. How do you know? It's positive. If it's positive, then it is a spontaneous reaction. Had I set this up in the other direction and added positive 0.13 to negative 0.74, we would say that it is not spontaneous. So another quick way to write these cells, and you can do this with batteries as well, is to use something called line notation. So in this form, what you do is you set up the anode on the left-hand side, followed by its aqueous solution. And then the right side has the aqueous solution, and then finally the metal cathode. So over here will be your anode, and over here will be your cathode. And in between will be your solutions. This double thing in the middle represents your salt bridge. And it doesn't matter what the salt bridge is made out of. It's just two lines. You don't have to write what it's made out of. So in this particular cell, you've got a magnesium anode, which is losing electrons, and an aluminum cathode that's gaining those electrons. And they're immersed in solutions of their ions. The aqueous is really not necessary, neither is the solids there on the magnesium and the aluminum. But if you're given them, you can go ahead and write them. Sometimes though, if they give you the concentrations of those, that will matter in the cell potential calculations, which we'll do later. So if they had said that it was 1 molar solution of these, you would write that it's 1 molar in parentheses next to the Mg2+, and I'll show you one of these. And 1 molar for the aluminum ions if they had told you what its concentration was. If they didn't say it, then you don't have to write it. But you do need to write them if they tell you what they are. So here we've got one where we actually are told what they are. This one, excuse me, is a little more complex. So it says a galvanic cell is composed of solid zinc as the anode. Okay, so they're telling us that. So I'll have zinc written here and draw a line. And then it says immersed in a solution of zinc ions. So, and it says 1 molar. So I'm going to write my zinc ion, Zn's always 2+, and they're told it's a 1 molar, we're told it's a 1 molar solution. And then I've got my salt bridge. And a cathode, which is an inert platinum electrode. So what I'm going to have over here is platinum written as my metal electrode for the cathode. And it's immersed in 1 molar hydrogen ions. So that would be H+ ions that are 1 molar. And then it is also with hydrogen gas bubbled at 1 atmosphere of pressure. So I would have H2, and I would write its partial pressure or concentration there. Usually that's a semicolon, but if you comma it, it'd be all right. And so what you've got here is it's transferring from zinc to Zn2+. So what I have is zinc losing electrons becoming Zn2+, and I'm moving across this way. And then I have the salt bridge, and then the hydrogen is gaining electrons becoming H2, and that's happening by use of a platinum electrode. It says calculate the cell potential for this. So if zinc is losing electrons, it would be zinc going to Zn2+ plus 2 electrons. And for the hydrogen, I have hydrogen ions going to hydrogen gas, which means that it's gaining, there's 2 of these, so it'd be gaining 2 electrons. And I would have to look up what those voltages are. Hopefully, the cell potential for hydrogen is 0. But if I scroll back up and look at zinc, let's go find zinc up here. Let's take these away. Here is my hydrogen electrode, of course, 0. And here is my Zn2+. And that is oxidized, so I'll flip it. So right here, this would be positive 0.76. So I'll go back down here to my system. Here we go. And this would be 0.76 volts. Sloppy. And so I'll add these together. My total cell potential, so this cell potential would actually be 0.74 volts. Oh, 76. Sorry about that. 0.76 volts. And then I can add these up here. I just have 2 electrons for both. So 2 moles of the hydrogen plus the zinc is going to produce Zn2+ and hydrogen gas. So let's see if we did everything they asked. Write the line notation for the cell and the half reactions. We did that. Calculate the cell potential. Yes. Indicate whether it's spontaneous. It's positive. Therefore, yes, it is spontaneous. Or it is thermodynamically favorable, which is actually what they'd like us to say. But that's fine. Yeah, it would be spontaneous. So here we go, kind of typed in pretty, but yeah, it would be 0.76 volts. So we're going to quit there. So we went through, let's see, we talked about the electromotive force. We also learned how to use how to write and draw a wet cell battery and calculate its cell potential. And then we learned how to use line notation. So I'll see you guys in the next video. We'll talk a little bit more about calculation of cell potential and how it relates to Gibbs free energy and calculation of cell potential when they're non-standard conditions as well. I'll see you in the next video.